current estimates for total U.S. electrical energy consumption is 4,137.1 terawatt hours in a year. How many years will it take for energy consumption to triple? Assuming either A, a linear growth rate of 10 to the 6 gigawatt hours per year, or B, an exponential growth rate of 4% per year, or C, a continuous exponential growth of 4% per year. So same growth, but just different model. So the givens in this problem is the initial quantity E0, 4,137.1 terawatt hours. And then we were given the linear growth constant, K, of 10 to the 6 gigawatt hours per year. We are given exponential growth constant, which is alpha. Let's see, this is an exponential, so we'll give it an alpha sub exp just to differentiate the two. That's 4% per year. And then we've got alpha continuous exponential, and that also is 4% per year. We are asked to find T when the final quantity is equal to 3 times the initial quantity, or E0, not EI. The solution to this is just to apply the growth rate formulas from the text. The linear growth rate formula, which we'll use in part A, is Q equals capital K times T in years plus Q0. In our case, that's E final is equal to K times T plus E0. Just Q, remember, is a random placeholder for any quantity, Q quantity. E, we're specifically looking at energies here, so in this case we want to sub in this relationship, so 3E0 is equal to KT plus E0. So that's 3 times this value here, 4,137.1 terawatt hours is equal to 10 to the 6 gigawatt hours per year times however many years in T it takes to get there, which is what we're solving for, and then we want to add on the initial quantity of 4,137.1 terawatt hours. So we got that. So now I just need to subtract this number from that number. I'm left with 8,274.2 terawatt hours, and that's just equal to 10 to the 6 gigawatt hours per year times the number of years. So if I want to solve for T, I have 8,274.2 terawatt hours divided by 10 to the 6 gigawatt hours per year, and then if I do that I'm going to be left with terawatt hours per gigawatt hour, so I need to do some cancellations, and that's 1,000 gigawatt hours per terawatt hour. So throw that in there and everything will cancel out, and we're left with 8.2742 years as our answer, which we box. All right, so we were asked to find T. There it is. In B, we were asked to apply the exponential model. That is that the final amount of energy is going to be equal to the initial amount of energy times 1 plus alpha, where alpha is the growth constant raised to the power of T. And so in this case we're going to have, sorry about that, must have hit an app there, 3EF is equal to, sorry, not 3EF, 3E0 is equal to E0 times 1 plus alpha T, I could go ahead and insert the value of E0 if I wanted to, but you can see I'm just going to divide and it's going to fall out of the equation anyway, so I'm not going to even do that. This just leaves me with 3 is equal to 1 plus alpha t. I want to get to t. It's in an exponent. I don't want it in an exponent, so that means I need to get it out of the exponent. The technique to do that's the natural log. So I'll take the natural log of 3, and that's going to be equal to the natural log of 1 plus alpha. There, it's not written very well. 1 plus alpha quantity to the t. We know the property of a natural log is that pulls the exponent down as a multiplier in front, so we've got the natural log of 3 is just equal to t times the natural log of 1 plus alpha. I now can isolate t as t is equal to the natural log of 3 divided by the natural log of 1 plus alpha. Now it makes sense to go ahead and sub in my quantities. Natural log of 3 divided by the natural log of 1 plus the alpha, which in this case was the value specified for the continuous growth model, 4%. In a decimal form, that's 0.04. So there we have it. And we divide natural log of 3 by natural log of 1.04, and we get 28.011 years for t. So that was for an exponential growth rate. To finish off the problem, we need to repeat it for a continuous exponential growth model. So that in C is the final value is equal to the initial value times e to the alpha t. So that's continuous exponential, involves the natural number e. And so again, we just get 3e0 since we're looking for the tripling time. That's equal to e0e to the alpha t. Same process pretty much. We're going to divide both sides by e0. That leaves us with 3 equals e to the alpha t. Ln of 3 is equal to the ln of e to the alpha t. What you should know about that is the natural log undoes the natural number, so we're left with the natural log of 3 is just equal to alpha t. And so t is equal to natural log of 3 divided by the continuous exponential growth constant. That's ln of 3 divided by 0.04. And that's going to give you a value of t equals to 27.4653 years. So that rounds off the problem.